As I've said, distance-based methods are based on the very simple idea of taking a multiple alignment, counting all the pairwise genetic distances between each pair of sequences. This will give you a distance matrix, and then based on that distance matrix, try to find a tree such that the distances measured along the tree corresponds to the distances you observed from the alignment, the distances in your distance matrix. So how do we actually do that? In the exercise, in the weekly quiz that you did, you were able to do that manually because it was a very small example. But again, like for other problems that we're looking at, if we look at real-sized problems, of course, we will need something more robust. We will need a recipe. We will need an algorithm so we can get a computer to do the work for us. For real-sized data sets, it will not be possible to do this manually. We need some sort of recipe so that a computer can do it for us. How would we do that? That's what I'm going to explain in this part of the lecture. Well, to return you to what we are talking about, the idea is we have a set of sequences. We try to build a tree and find some branch lengths such that the distances measured along the tree correspond to the distances we observe from the alignment. The goal, as I said, was to find branch lengths such that the tree distances, the patristic distances, are as close as possible to the observed distances. And what did I actually mean when I say, what do I mean when I say as close as possible? Well, one way to define what I mean is to use this expression, and that's what people usually do in phylogenetic reconstruction. This expression tells us that this measure Q is what we call the sum of squared differences. It's really not as frightening as it may look to some of you because of the summation sign. The idea is quite simply that for each pair of sequences in our data set, we take the observed distance, indicated by uppercase D, for that pair of sequences, subtract the tree distance for that pair of sequences, which we find by adding branch lengths along the tree. We take the difference between these two, the observed and the tree distance, square that difference, do the same for all the other pairs, and add up all of those terms. So you can see that if the observed distance and the tree distance are exactly the same, then this will be 0. 0 squared will still be 0, and 0 plus 0 plus 0 will of course be 0. So in the case where it's possible to find a perfect match, where each tree distance corresponds to the observed distance for that pair of sequences, then this measure will be 0. That's the best of all possible worlds. However, as I said, for reasons that I'll return to, sometimes it's not possible to find that exact match. What we then want is we want to find the branch lengths such that this measure Q becomes as small as possible. We want to minimize Q, and we say then that these are the best branch lengths for this particular data set. How do we do that? Oh, and one thing I should maybe mention. So one measure is the sum of squared differences as indicated on this slide. There are other ways of measuring what we mean when we say as close as possible, and one measure that you may run into in some software is exactly the measure I just mentioned, except where each term has been divided by the length of the branch that we're looking at, by the observed distance between those two sequences. The idea with this is that there's probably larger error on longer branches, so we should somehow normalize. And dividing, if you have two sequences that have a very large genetic distance, then we should downweight the error term from that branch, and we do that by dividing by the distance between those. We can divide either by the distance itself or maybe by the distance squared. Both methods are in use, and you may run into them in some software. But for now, let's just focus on the original formula that I gave you here. The sum of squared differences we take for each pair of sequences, the observed distance, subtract the tree distance, square it, add up those terms, and the goal is to try to find branch lengths such that this measure becomes as small as possible. So let's just look at an example to see exactly how that's done in a computer, because it turns out that there's actually a mathematical analytical solution to that, and I'm going to try to walk you through how that works. Let's look at an example. We start out with a multiple alignment of 4 sequences. As I say, from those 4 sequences, the first step is always to construct the distance matrix. For each pair of sequences, we go in and we count how many differences are there between those 2 sequences, and then put that number in the distance matrix. I've done that on this slide. Once we've done that, we forget all about the original sequences. We just care about the distance matrix because that's what we're going to use as the basis for building now our phylogenetic tree. So the goal is, as I say, to find a tree where we place the sequences on the leaves and then find some branch lengths. The goal is to find these branch lengths such that the tree distances, the metristic distances, are as close as possible to the observed distances. So there are a number of different ways in which sequences can be placed on a tree. In this particular tree, I've taken sequence 1 and 2 and placed together. When that's the case, then the tree distances correspond to sums of branch lengths as indicated on this slide. Now, how would we find the best branch lengths for this particular tree? Let's say this is not necessarily the best tree, but if we're looking at this particular tree, how would we find the best set of branch lengths for that particular given tree? Well, as I say, the goal is to minimize this measure Q, the sum of squared differences. So sum of squared differences is for each pair of sequences the observed distance, uppercase D, minus the tree distance, lowercase d, squared and summed. If we write that out in full for all the pairs of sequences, it will look as on this slide. We have in this case sequence 1 and 2, observed distance, minus sequence 1 to 2, tree distance, squared, plus the observed distance minus for sequence 1 and 3, minus the tree distance for sequence 1 and 3, squared, etc., for the rest of each pair of sequences here. We have 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. Those are all the pairs of sequences in our data set. So this is an expression for Q. This is the sum of squared differences written fully out without the summation sign. Now in this expression, we know that the tree distances, the distances measured along the tree, in fact correspond to some sums of branch lengths. If we take this expression and then for each tree distance substitute the corresponding sum of branch lengths, then it will look like this. Sequence 1 to 2, the distance measured along the tree is the same as A plus D. So instead of writing minus the tree distance for 1 to 2, we would say minus A plus D. If we lift the parentheses, we put in minus A minus D in the first parenthesis here. Similarly, sequence 1 to 3, measured on the tree, that's A plus B plus C. So instead of lowercase d 1, 3, we now put minus A minus B minus C. The rest of the terms we do similarly. This expression we can now simplify by, instead of the uppercase d's, putting the numbers we actually observed. Uppercase d's, I remind you, are the observed distances. So instead of uppercase D 1, 2, we can put the actually observed distance, which was 2. Instead of 1, 3, we put 9, etc. So this is now an expression for how Q, the sum of squared differences, depends on the branch lengths. Let's just move that to a new slide so we have more space to work on. This is how Q depends on these 5 branch lengths. And I remind you that the goal here is to find these branch lengths. We don't know what the branch lengths are. We're trying to find good values for these branch lengths such that this value becomes as small as possible. That's the problem we're trying to solve here. How could we move on with this? Well, let's try to work on this expression a bit. First, we can expand it by multiplying out all of these squared parentheses. If we do that, we end up with this rather unwieldy expression. You can see that we have a lot of terms with that are just numbers, some terms with A, some terms with B, C, D, and E, some terms where we have C and E and A and D, etc., and some terms where we have A squared, D squared, B squared, etc. This is how Q depends on all of these branch lengths. And the goal, as I say, is to find good values for the branch lengths. How do we do that? Well, let's do it one branch at a time. Let's start by focusing on how Q depends on branch length A. So if we start by collecting all the terms with A up front, then we get this expression. First, 3 times A squared, we have that somewhere here, there, so we put that up front. Then we have a number of terms where we have A, just plain A, inside. Okay, so we have minus 38 times A, we have 2 times A times D, 4 times A times B, etc. If we take all of the terms with A in them and put them together and then move A outside of the parentheses, it'll look like this. After we've done that, we have a whole bunch of terms down at the end here which do not contain A. Okay, so what is this expression telling us about how Q depends on A? Well, to understand that more clearly, let's say for now that we're keeping all the other branch lengths, that we're keeping B, C, D, and E constant. We have fixed them at some arbitrary value, and now we're just trying to understand how does Q depend on A if we vary A across the possible values that A can have. Well, look at this. We have 3 times A squared, then we have some constant times A. Remember, we have now just fixed these branch lengths at arbitrary values, so we have some constant times A, and then we have some constant. 3 times A squared plus a constant times A plus some constant. You know what that is? That's a parabola. So Q shown as a function of branch length A will look like this. Our goal, I remind you, is to find value of branch lengths that minimize Q. In this particular case, that means we need to find the value of A which is at the bottom of this parabola. We need to find the minimum of the curve. As you will probably recall from high school math, the way to find a minimum of a curve is done by differentiating the function for that curve and finding the place where that differential is 0. The differential of a function with respect to A in this case, dq dA, is the same as the slope of this curve. And we are trying to find the place where the slope is 0, which in this case will be the minimum. As it turns out, it's a fairly simple differential to compute. We have here Q as a function of A. If we differentiate that with respect to A, 3 times A squared differentiated with respect to A, the 2 moves down, so we have 6 times A. Then we have a whole bunch of constant terms here, times A differentiated with respect to A is just the constant terms. Then we have a whole range of other constant terms down here that are not multiplied by A. They disappear out of the differential. So saying that the slope should be 0 is the same as saying that this expression should be 0. The best value for A in this case can be found is a solution to this particular equation. Now, we could do the same for all the other branch lengths. We could do just like we did for A here, we could do the same for B. Collect the terms with B up front. It would be, it turns out, a similar expression, something times B squared, something times B plus something. It's a parabola. Again, we would have to find the minimum by differentiating. All in all, the way that for each of the 5 branch lengths, we can find the minimum of the curve by doing a partial differentiation of Q with respect to that branch length. In each case, those differentials can be computed in symbolic form, giving us these expressions for the differentials, for the slopes of the curves. And as I say, our goal here is to find the values of these branch lengths where we are at the minimum simultaneously of all of these curves. That can be solved by setting all of these equations equal to 0. So this is 5 linear equations with 5 unknowns. That's something that can be solved using ordinary mathematical techniques. I'm not going to go into that here. You've probably done it yourself. And as it turns out, for this particular set of values that we were looking at, the solution is this. A equals 1, B equals 5, C equals 3, D equals 1, and E equals 2. So for the particular set of data that we have here, for the particular distance matrix, and for the given tree that we had, there's an entirely analytical solution which will give us the best possible branch lengths for that tree. If we put them on the original tree, A equals 1, B equals 5, C equals 3, D equals 1, and E equals 2, you will see that in this case it actually matches our distance matrix exactly. The distance from 1 to 2 is 1 plus 1. That's 2, just like we had in the original distance matrix. From 1 to 3, it's 1 plus 5 plus 3, that's 9. That also fits. 1 to 4 is 1 plus 5 plus 2, that's 8. 2 to 3, 1 plus 5 plus 3, that's 9. 1 to 4, 1 plus 5 plus 2, that's 8. And finally, 3 to 4 is 3 plus 2, that's 5. So in this particular case, using the analytical apparatus here, we have found the best set of branch lengths, which in this case, it turns out actually solved the problem exactly. This would give us a Q of 0, the absolute smallest possible value of Q. This means that there is a way, if we have, this makes it actually possible to write a computer program that will find the best distance tree. The main idea in this, we have an alignment with a set of sequences, let's say 10 sequences or whatever. The idea is that a program that will find the best tree should look through all the possible tree topologies for 10 sequences. There are a great many, as we'll return to. As we already saw, there's a great many possible tree topologies for 10 different sequences. But still, we want the method to look through all the possible tree topologies. For each investigated tree, it should then find the best branch lengths, and it should do that using this least squares criterion we just looked at, solving these n equations with n unknowns. That's possible. For any possible tree, it's possible to find the best branch lengths, and therefore also compute the value of Q. After we've done that for all the possible trees, we can then select the best tree as being the one having the smallest sum of squared errors, the smallest sum of squared differences. In this case, we used the least squares criterion to find the best branch lengths, and we used the least squares criterion to select the best among the trees. This is what we call, therefore, not surprisingly, the least squares optimality criterion. You will try in the exercise to use software that does that. There is another way of building trees, which is called minimum evolution. It's very similar. Again, the idea is to look through all possible tree topologies. Again, the idea is for each investigated tree to find the best branch lengths using these n equations with n unknowns, meaning we use the least squares criterion. But then instead of picking the tree that has the smallest Q, you instead end up picking the tree with the smallest sum of branch lengths. So this step is more like parsimony. We pick the smallest tree, the tree assuming the least amount of mutations. So in this case, we use the least squares criterion for finding the branch lengths, but we use the minimum tree length as the criterion for selecting the best tree. This is called minimum evolution. You will probably run into that in software now and then. In fact, minimum evolution and least squares typically give quite similar trees, but there will be smaller differences sometimes. So at the end, there's just one thing I would like to mention, and that is that, as I say, it's not always possible to find a set of branch lengths such that the tree distances and the observed distances match exactly. And you might wonder, how is that? I mean, because the sequences have been evolving, so if we knew the real history, why couldn't we just put that in and we would get the right tree? The reason that it's not possible to have the observed distances, the distances observed by comparing sequences, fit the tree exactly, is the phenomenon of superimposed substitutions or multiple substitutions. Any given site in a DNA sequence can mutate more than once, but we can only observe one difference. That's the essence of the problem here. So imagine, for instance, that we have a sequence, as on this slide, that's evolving. Position number 1 mutates to a C, and then mutates to a G. There's a couple of positions that don't change. This position, this G, mutates to a T, and then mutates back to a G. Finally, on the last position, the C mutates to an A. Now, if you compare this final sequence to the original sequence, you will see that they differ on 2 locations. We can observe 2 mutations having taken place. But in fact, 5 mutations have occurred. So this means that since a single site can mutate more than once, but we can only observe one difference per site, then we will always underestimate distances. Here we have 5 actual distances, mutations. We can only observe 2 events. This problem, of course, gets worse the larger the distance. So if you have a sequence that's only 50% identical to another sequence, then a lot of the positions in that sequence will have mutated more than once. So in that sense, the distance is larger than 50%. And this is why it's not always possible to find the exact match. As it turns out, it's actually possible to correct for this. But in order to do it, you need to make some assumptions about how evolution occurs. I'll just very briefly mention the idea. The goal is that we have an actual data set, we have a multiple alignment, we have some observed distances, and our goal is that we want to try to infer the real number of mutations from the observed number of mutations. The only thing we have to work with is, in terms of data, is the sequence alignment. We have our observed data there. In order to infer this, we therefore need to make some assumptions about how evolution occurs, a model of how evolution occurs. There are different possible models that we could use, and I'm just mentioning this now. We'll return to these models later when we talk about likelihood. There are different models, different hypotheses you can have about how sequences evolve, and depending on what hypothesis you have about how your sequences have been changing, you will make different inferences about the actual number of mutations. The simplest model that we'll look at is called the Jukes and Cantor model, after the gentleman that originally developed this model. The idea is quite simple. The idea is that any possible substitution, A to C, A to G, A to T, etc., occurs with the same rate. There's the same probability that an A will change to a G as that it will change to a T, etc., etc. Under this model, it's also assumed that the 4 nucleotides have the same frequency, 25%. And it turns out that under these conditions, same frequency of all nucleotides, same rates for all possible substitutions. If you sit down and do the math, you can come up with this formula that tells you what the actual distance must be based on the observed distance. And I'm not going to go through how you end up with this equation. You can read about this in various molecular evolution books. Bottom line is, for any observed distance, you can plug your number into this formula and then get an estimate of the actual distance between the sequences. For instance, in this particular case, if you plug in the distance 0.42, then you get out the real distance 0.64. Note that now I'm no longer using absolute distances. I'm not counting the number of mutations. These are relative distances. The relative distance is just the absolute distance divided by the length of the alignment. So a relative distance of 0.42 means that 42% of the positions in the sequence have changed.